Welcome you all in the lecture number 7 of Abstract Algebra MTL 6051. In this lecture, we will going to discuss what is the coset, what is normal subgroup, and factor group or quotient group. Right? We have already discussed what is the subgroup of any group. Right? A non-empty set H phi does not equal to H. H is subset of G where G is group with respect to this operation. Then H is subgroup of G if H with respect to this operation is itself group. Right? If this is group, then this is known as subgroup of G. Right? Now, using the concept of subgroup, we will discuss what is the coset. Right? We will discuss what is the coset. If H is subgroup of G, H is subgroup of G, then coset is defined as follows. A of H, that is AH, A belongs to G, and what is H? H is element of capital H. Right? The collection of all the elements of the type AH, right, is denoted by the set AH, right, this form, and this is known as coset. Right? A operated from the left side of H, then this coset is known as left coset. And similarly HA, A operated on the right side, that is small HA, where H belongs to capital H and A belongs to G. This is the coset and known as right coset. Right? See the definition. AH is equal to A into H. H belongs to capital H. And what is A? A is element of G. Right? What is A? A is element of G. Similarly, HA is equal to small HA. H belongs to capital H and A belongs to G. Right? These cosets are known as AH is left coset and HA is right coset. Right? But one thing is important. We define coset when H is subgroup. Right? When H is subgroup. See the result. If G is abelian, then its left coset and right coset are equal. Right? If G is abelian, then what is AH? AH is equal to HA. This type of element in left coset AH and this type of element in right coset HA. If group is abelian, then AH is equal to AHA. This is the property. Now, see one example. If Z is equal to Z6, what is Z6? Z6 is group with respect to addition modulo 6. It means it contains 0, 1, 2, 3, 4, 5. This with respect to addition modulo 6. This is group. And let H is equal to 0, 2, 4. This is subgroup of Z6. Right? Then what are the cosets? What are the coset of H in Z6? Say what is A? A belongs to G. Then what is EHA? EHA or AH? This is EH of A. EH belongs to capital H. Now see, A belongs to G. What is G? G is Z6. What is EH? EH is this 0 to 4. Then let us consider any element of Z6. Let 0 belong to Z6. Then 0 plus H is equal to 0 plus what is H? 0, 2, 4. This can be written as 0 plus 0, 0 plus 2 and 0 plus 4. What is 0, 2, 4? This is nothing but H. Right? Similarly, 1 belongs to Z6. Then 1 plus H, that is 1 plus 0, 2, 4. And this is equal to 1 plus 0, 1, 1 plus 2, 3. And 1 plus 4 is 5. 1, 3, 5. Right? This 1, 3, 5 does not equal to H. Okay. Now 2 belong to Z6. Then 2 plus H is equal to 2 plus 0, 2 plus 2 and 2 plus 6. What is 6? 6 is equivalent to 0 in modulo 6 operation. Then this is 2, 4, 0. Right? This is H. And 3 plus Z6 is equal to 3 plus H is equal to 3 plus 0, 3 plus 2 and 3 plus 4. Right? This 3 is okay, 5 is okay, but 7 is greater than 6. Divide 7 and obtain the remainder. If we divide 7 by 6, then remainder is 1. This is 351. Similarly, 4 belong to Z6, then 4 plus H is equal to 4, 6 and 8. 4 is okay, but 6 divided by 6, remainder is 0. 8 divided by 6, remainder is 2. Right? And this is 0, 4, 2. This is H. Similarly, 5 belong to Z6 is 5, 1, 3. This is not equal to H. Then, see, where we obtain H? We obtain H at following places. H, this is H and H. Right? We obtain H when the element A belongs to H. It means, see, 0 is the element of Z6, but 0 is also element of H. 2 is element of Z6, but 2 is also element of H. 4 is element of H. Right? If it means, result says that if A belongs to H, then AH is equal to H. Right? If we form a coset by the element of H, then it is nothing but H. Why? Since H is subgroup of G. Right? If A does not belong to H, if A does not belong to H, then AH does not equal to H. Okay? Now, we already studied in our BSc class that if AH and BH are distinct coset, if AH and BH, right? We studied that two cosets are either disjoint or identical. Two cosets are either disjoint or identical. Right? Disjoint means AH intersection BH is equal to 5. And identical means AH is equal to BH. It means if we have two coset AH and BH, then they have the relation. Either they are equal. If they are not equal, then AH intersection BH is equal to 5. This is this result. Right? Now, Form the coset for S3 where H is given by I and cycle 1 2. Cycle 1 2 means we already discussed this, that is 1 2 3, 1 is 2, 2 is 1 and 3 is 3, right? Image of 1 is 2 and 2 is 1 and 3 image of 3 is 3, right? This is the permutation. Then what is H? H containing two permutation, one is identity and second one is 1 2, right? Then we have to find out the coset of this H in S3, right? See, I, what is I? I in S3. If we form coset IH, what is IH? IH is H. Since I belong to H, similarly 1 2 belong to S3, then what is 1 2H? 1 2H is H. Okay. Okay. Now let us see other element. What are the other element of S3? Other element of S3 is 1 3. 1 3 belong to S3. Now 1 3H. What is 1 3H? That is 1 3I and 1 3 1 2. Right? What is 1 3I? 1 3I is 1 3. And what is 1 3 1 2? 1 3 1 2 is 1 2 3. How? What is 1 3? 1 3 is image of 1 is 3, 3 is 1 and 2 is 2. This is 1 3. And what is 1 2? Image of 1 is 2, 2 is 1 and 3 is 3. Right? Now compose these two permutations. Image of 1 is 2 and 2 is 2. This is 2. Image of 2 is 1 and 1 is 3. This is 3 and this is 1. Right? Form the cycle of this permutation. 1, image of 1 is 2, image of 2 is 3 and 3 is 1. This is 1 2 3. Right? Then second element is 1 2 3. Right? See here, 1 3H is equal to 1 3 and 1 2 3. Right? This one. Similarly, 2 3 belong to S3. Then 2 3H is equal to 2 3 and 1 3 2. And 1 2 3 belong to S3. This is 1 2 3 and 1 3. And 1 3 2H. This is 1 3 2 and 2 3. Right? Solve this problem. If you have any doubt, then you can ask me. Next, before going to factor group or quotient group, we have to discuss the normal subgroup. Right? Only overview of the normal subgroup. What is normal subgroup? A subgroup H of G is said to be normal. Right? If its left coset and right coset are equal. What is H? H is subgroup. H is subgroup of G. Then if AH is equal to HA, if both are equal, then H is normal subgroup of G. This is notation of the normal subgroup. Then H is normal subgroup of G. Right? Now see the example. What is the example? If group is abelian group, then every subgroup is normal subgroup. Why? Since if group is abelian, then AH is equal to HA. It means A of for all A. It means AH is equal to for all A belong to G and for all H belong to H. Right? If G is abelian, then this condition hold and this condition hold. It means H is normal subgroup of G. What is alternative group? AN. AN is normal subgroup of ASM. Right? We studied one result that if index of any subgroup in the group is 2, then this H is normal subgroup of G. It means if order of G by H, this is 2, then H is normal subgroup of G, right? And this 2, it means order of G by H, this one is known as index, right? Then H is normal subgroup of G, and so by using this result, what is order of Sn by An? This is equal to 2. Therefore, by this result, An is normal subgroup of Sn. Okay. Similarly, SL2R, right? SL2R. SL2R. What is SL2R? 2 cross 2 matrices whose entries are real and determinant is 1. Remember that determinant is 1. And what is GL2R? All 2 cross 2 matrices entries are real and determinant is not 0. Not necessarily 1, but determinant is not non-zero. Then this SL2R is subgroup of SL2R is normal subgroup of GL2R. Why? Let small h belong to SL2R. Then what is the condition? X inverse, right? If we prove that this type of element in SL2R, right, for all x belong to GL2R, then SL2R is normal subgroup of GL2R, right? But how we prove this, that this element belong to this? See, the determinant of X inverse, this is equal to determinant of X, determinant of H, and determinant of X inverse. What is H? H is element of SL2R. Therefore, this determinant is 1. Since SL2R containing all element whose determinant is 1, and this is determinant of X. And what is this? Determinant of X inverse, right? And this is equal to determinant of X into determinant of X whole inverse, right? Then this is A and A inverse. This is 1. It means determinant of this thing, determinant of this X inverse, this is 1. It means X inverse belong to SL2R, right? Hence SL2R is normal subgroup of GL2R, right? This is the result. If H is subgroup of G with index 2, then H is normal subgroup of G. Prove it. This is homework for you. Now see, let us consider G is equal to S3 cross S4. S3 symmetric group of order 6 and S4 symmetric group of order 24, right? Order of this is factorial 3 and order of S4 is factorial 4, right? This is 24 and this is 6. Then what is order of this? Order of this is 6 into 24. This is 144, right? Then if we consider H A3S4, what is H? It's subgroup of, this is subgroup of G. Then this H is normal subgroup of G. Why? Evaluate order of G by H. What is order of G by H? What is G? S3 cross S4. And what is H? A3 cross S4. What is order of S3 cross S4? 144. What is order of A3? Order of A3 is order of S3 by 2. What is order of S3? 6. 6 by 2, that is 3, into what is order of S4? 24. And what is this? This is 2. Then above result says that if index is 2, then this H is normal subgroup of G. It means A3 cross S4. It means that A3 cross S4 is normal subgroup of S3 cross S4. Right? Next. Next, find all normal subgroup of quaternion group Q4. What is Q4? We know that Q4 is equal to plus minus 1 plus minus I plus minus j and plus minus k. Right? Then what is H1? We start with the smallest subgroup E. E means identity, that is 1. That is 1. What is H2? 1 and minus 1. What is H3? 1 minus 1 I minus I. What is H4? 1 minus 1 j minus j. What is H5? 1 minus 1 k minus k. What is H6? H6 is Q4. Right? These two subgroups, these are known as trivial. And except these two, all are known as, these are known as non-trivial subgroup. What is this? Non-trivial subgroup. Right? Non-trivial subgroup. It means Q4 has 4 non-trivial subgroup and 2 trivial subgroup. Every group has 2 trivial subgroup, right? And in fact, they are normal also. Next, find all the normal subgroup of S3. See, what are the subgroup of S3? What is S3? S3 is this. We already discussed in previous lecture. Now, consider H1. H1 is identity, right? H1 is identity. And first evaluate two normal subgroup, right? H1 is identity. This H1 is identity. And next one is S3 itself. These two are trivial. Now find out other groups, right? Then other groups are, what is H2? H2 is equal to identity and 1, 2. This is subgroup. And whether it is normal or not, we will see later. What is H3? I 1, 3. What is H4? I 2, 3. What is H5? I 1, 2, 3 and 1, 3, 2. Right? These are the non-trivial subgroup. Non-trivial subgroup of ES3. Now, no doubt H1 and H6 are normal, right? Since I already told you, every group has two normal subgroup. One is identity and one is group itself, right? Check whether the other group are normal or not. Now, first see H5. What is order of H5? Order of H5 is 3. Then, what is order of S3 H5? That is 2. Why? Order of S3 is 6. Order of H5 is 3. 6 divided by 3, that is 2. Then index is 2. Index is 2. And result says that if index is 2, then H5 is normal subgroup of S3. It means this H5 is normal subgroup, right? It is normal subgroup of S3. Okay. Now check whether H2, H3, H4 are normal or not. Right? Evaluate only one. See, consider H2. Right? Consider H2. I and 1, 2. Now, if it is normal, then X, H, X inverse belong to H. And what is H? H is I and 1, 2. Right? Let X is equal to 1, 3. Then 1, 3. H consider 1, 2. And X inverse say 1, 3 inverse. What is X? X is 1, 3. What is H? H is 1, 2. And what is X inverse? X inverse is 3, 1. Right? Then solve this. If we solve this, then what is this? This is 1, 3, 2. Right? Check. 1, 2, 3. And this is 3, 1, 2. And 1, 2. And next 1, 2, 3. 3 is 1. Image of 3 is 1. And 1 is 3. And 2 is 2. Right? Then apply first 2. First 2 is 1, 2, 3. Then one image of 1 is 3. 3 is 3. 1 is 3. 2 is 2. 2 is 1. 1. 3 is 1. 1 is 2. Right? Then combine this with this. This is equal to 1, 2, 3. And solve this. Image of 1 is 3. 3 is 1. 1. Image of 2 is 1. And 1 is 3. Right? And image of 3 is 2. And 2 is 2. Right? Then this is equal to 2, 3. Sorry, it is equal to 2, 3. No? But 2, 3 does not belong to H2. This does not belong to H2. Hence H2 is not normal. H3 is also not normal. This is also not normal. Then this H3 have 3 normal subgroup. H1 is normal, H6 is normal, and H5 is normal. But H3 have only one non-trivial normal subgroup, that is H5. It means I, 1, 2, 3 and 1, 3, 2. Okay. Next. What is factor group? Factor group, if G is group. What is G? G is group. And H is normal subgroup of G. What is G? G is group and H is normal subgroup of G. Then construct G by H. What is G by H? G by H, element of G by H, either this type, HA, A belongs to G, right? Or elements of G by H, AH, A belongs to G, right? Then this G by H, this forms group. Group with respect to which operation? With respect to operation defined as follows: AH, one element, and BH, another element. AH and BH are element of G by H. Then operation between them, this is ABH, right? With respect to this operation, G by H, with respect to this operation, forms group, and this group is known as factor group or T-quotient group. This group is known as factor group or quotient group, right? See one example. What is G? G is set of integer. set of integer with respect to addition is group. Now, what are the subgroup of Z? We already discussed in our previous lecture that subgroup of Z is the type of MZ, right? This is the subgroup of Z plus, right? In this case, what is M? M is equal to 4, right? 4Z. Then, what are the element of this factor group? Factor group G by H means, what is G? G is Z. What is H? H is 4Z. G by H is Z by 4Z, right? See the element. Elements of G by H is AH, A belongs to H, or this can also be written as A plus H, right? If G plus is group, remember that if G is group with respect to addition, then A plus H, A belongs to G, A belongs to G, right? Then what is Z by 4Z? This is equal to A plus Y plus, since Z is group with respect to addition, whatever be the operation, this operation come here, right? We will write here A plus 4Z and A belongs to Z, right? This type of element Z by 4Z have. Now see, A belongs to Z. Let A is equal to 0 and 0 belong to Z. Then 0 plus 4Z. What is 0 plus 4Z? 0 plus 4Z is 4Z. Right? What is 4Z? 4Z is 0 plus minus 4 plus minus 8 plus minus 12, that's 1. This is 4Z. If we add 0 in every element of 4Z, then what we obtain? 4Z. Now 1 plus 4Z, right? 1 plus 4Z means 1. This is minus 3 and 5, minus 7 and 9, this type of element, right? 1 plus 4Z. 2 plus 4Z, 3 plus 4Z. And again, what is 4 plus 4Z? This 4 is equivalent to 0, right? Check. 4 plus 4Z, you obtain same as 4Z. See how? See how? 4 plus 4Z means 4 plus 4Z. What is Z? 4Z. 4Z is this one. 4Z is this, right? Add every element 4 in 4Z. Then 0 plus 4 is 4. 0 plus 4, 4 plus 4 is 8. And 4, see here 2 element, plus 4 and minus 4. 4 minus 4 is 0. 4 plus 8 is 12. 4 minus 8 is minus 4. 4 plus 12 is 16. 4 minus 12 is minus 8. Right? That's 1. Now see, this set and this set and this set, this 4Z, they both are equal or unequal, right? 4 plus 4Z is equal to 4Z. 4 plus 4Z is equal to 4Z, right? Then the 4Z by 4Z containing 4 elements, 0 plus 4Z, 1 plus 4Z, 2 plus 4Z and 3 plus 4Z, right? Then what is order of Z by 4Z? This is 4, right? Then Z by 4Z is cyclic. If it is cyclic, then it is isomorphic to Z4, right? This is isomorphic to Z4. Similarly, Z by tangent is isomorphic to Z10. Now it is homework for you. Find all elements of Z by tangent, right? Next, if G is equal to Z10, see what is G? G is equal to Z10. Z10 means it is group with respect to addition modulo 10, right? Z10 is group with respect to addition modulo 10. This is group, right? Then consider H. What is H? H is 2, right? What is 2? 2, 4, 2 plus 2, 2 plus 2, right? 2 first 2, then 2 plus 2 modulo 10. This is 4. Then 2 plus 2 plus 2. This is 6. Right? Again 2 plus 2 plus 2 plus 2. All are modulo 10 operation. This is 8. Right? And 2 plus 2 plus 2 plus 2 plus 2. This is 10, 10, 10. Right? And this is 10 modulo 10, that is 0. Right? It means we obtain 0, 2, 2 plus 2 is 4, 2 plus 2 plus 2 is 6, and 2 plus 2 plus 2 is 8. 2 plus 2 plus 2 plus 2 is 8. Right? Then this is 2. This is H. Now what is the element of Z? What is the element of Z10? Right? By 2. And this is equal to element of this is type A to what is A? A is element of Z10. Okay. Now see, what is element of A? A is element of Z10. And what is the element of Z10? Element of Z10 is this, 0 to 9, right? Then what is first element? 0 plus 2. 0 plus 2 is equal to 0. And what is 2? This 2 is 0, 2, 4, 6, 8. 0, 2. This one is 0, 2, 4, 6, 8. Add this 0 to every element. 0 plus 0 is 0. 0 plus 2, 2. 0 plus 4, 0 plus 6, 0 plus 8. Okay. Now, what is 1 plus 2? 1 plus 2 is 1 plus, this is 2. Right? Then this one is equal to 1 plus 0, 1, 1 plus 2, 3, 1 plus 4, 5, 1 plus 6, 7, 1 plus 8, 9. Okay. This one is 1 plus 2. 2 plus 2, 2 plus 0, 2, 2 plus 2, 4, 2 plus 4, 6, 2 plus 6, 8, and 2 plus 8. 2 plus 8 in modulo 8, that is 0. This is 0 plus 2. This one is nothing but 0 plus 2. Similarly, 3 plus 2 can be written as 1 plus 2. You can solve it and you find it that this is nothing but 1 plus 2. Check here. Now 3 plus 2. And what is 2? Element generated by 2. 0, 2, 4, 6, 8. And this one is equal to 3 plus 0, 3. 3 plus 2, 5. 3 plus 4, 7. 3 plus 6, 9. 3 plus 8, 11. 11 divided by 10, that is 1. Right? And this one is nothing but 1 plus element generated by 2. Right? This one and this one. This is 1 plus 2. And 4 plus 2 is 0 plus 2. 5 plus 2 is 1 plus 2. Right? It means check all the element this and these element. These are nothing but only two element. One element is 0, 2 and 1, 2. Right? Only these two elements. Then what is Z10 by 2? This is the two element only, 0 plus 2 and 1 plus 2. And what is this? This is isomorphic to Z2. This is isomorphic to Z2. Now, this is all about the factor group. In next class, we will discuss what is the center of the group and what is the centralizer of the group. Okay, we will stop here. Next class, we will discuss other topic. Okay, thank you.